Okay, so hi everyone, thanks Pavel for the introduction. So I'm a PhD student at MPI SWS in the group of Eva Darulova. And today I want to talk to you about our ongoing project to build a fully verified optimizing compiler for floating point arithmetic. But let's start things simple. So compiler verification has seen a big success story in the last years, where unverified compilers like GCC or LLVM give you no guarantees on the machine code that they spit out when provided an input program. Verified compilers like the CompCert compiler or CakeML for the verified implementation of standard ML will give you a proof that they preserve the exact meaning of the input program that you've given them in the machine code that they spit out, which is exciting. But let's look a little closer here, especially with a focus on floating points. So unverified compilers, as I mentioned before, GCC or Clang, they will not actually preserve IEEE 754 semantics. And they give you no guarantees on the result that they produced, but in turn can aggressively optimize your floating point program. And on the side of verified compilers, CompCert had this paper in 2015 by Bordeaux et al., where they extended the CompCert verified compiler with an implementation of floating points. And this was an amazing first step because the compiler fully preserves IEEE semantics with a formal proof, guarantees you to preserve the exact same meaning, but unfortunately, it cannot apply floating point optimizations. So there is a clear need here for supporting floating point optimizations in a verified compiler. And for the rest of my talk, I want to tell you about this ongoing project by kind of zooming in to two key parts of it, which is building a semantics that supports adding these optimizations to verified compilers and finding a way to reason about the optimizations that have been performed by the compiler. And I'll start by the semantics, where I would like to briefly speak about Icing, which is our new non-deterministic semantics for floating points, which we presented at CAF last year. And the key idea is that it gives you, one of the key ideas is that it gives you fine-grained control over where optimizations are applied. So this is the OPT annotation that we add here on this slide. Then it supports a subset of GCC's so-called fast math optimizations, so the ones it applies to floating point programs. And as an example on this slide, I'm showing you commutativity of multiplication at the bottom here, and FMA introduction, which replaces a multiplication and addition by the fused multiply add hardware instruction. And in our paper at CAF, we give implementations of three reference optimizers. The first one being an IEEE preserving translator, so kind of recovering the behavior you would have gotten from CompCert. And then a greedy optimizer that models kind of what you would get from GCC, so just greedily optimizing to its best possible, and a conditional optimizer, which tries to leverage some more knowledge you can get while optimizing. All of this is fully verified in the Hall 4 theorem provers, so we have correctness proofs for each and every step of the optimizations and for the semantics. And I want to briefly talk now about some of its key ideas for getting the optimizations to work. So the first one here is the value type that we use for Icing. In IEEE 754, if you take this example expression on the left-hand side and evaluate it, you get a floating point word representing the result in 64 bits, for example. But in Icing, what we do is, if we evaluate the very same expression, we produce a tree representation of the result. We call that a value tree representation. It allows us to carry information about the structure of the expression into the semantics by using a lazy data type for expressing floating point values. And how do we make use of this in the semantics? So if we take, again, just a simple example expression that we can optimize, so I added the OPT annotation here, and we use the example optimizations from before, what we're going to do is we say these optimizations are now included within a run of the semantics. So the semantics can non-deterministically optimize based on these optimizations. And with the fine-grained control, we limit where these are applicable. And there's 3 possible optimization results. So OPT1 here means that only optimization 1 has been applied. OPT2 means that only the second optimization was applied. And no OPT is kind of the IEEE 754 preserving result that you would get. And note that because we don't add commutativity of addition to the allowed optimizations, sorry, it will not be possible for the semantics to produce the result on the left-hand side of the slide. Putting all of this together, this makes Icing a direct fit for floating point arithmetic, giving you fine-grained control and supporting different styles of optimizations. But now to kind of step back a bit, what does this all mean for a compiler? So in Icing, we've integrated the Icing semantics into CakeML source semantics, which is one of the existing bigger verified compilers. And what we first prove is that from a run of deterministic CakeML source code, we can recover kind of a non-deterministic Icing execution by the correctness proof for the optimizers. So basically proving that the optimizer had to pick one of the possible results of running the Icing semantics. And from the CakeML compiler correctness theorem, we then get a proof that compiling this deterministic floating point code to x86 or ARM code has the exact same meaning. And now the question is this enough? Are we satisfied with this result? And I think it's missing one of the key points here, which is the roundoff errors. So let's look at an example. Let's say we have this Doppler floating point program that I'm showing you here on the slide. And suppose we again use some relatively simple example optimizations. This time I've swapped out the commutativity of multiplication for commutativity of addition and kept the FMA introduction. And let's say we can tolerate an error of 2 to the minus 10 of this program. So as a maximum roundoff error of the resulting program that we want to get from the compiler. If we optimize this with our Icing optimizer in CakeML, we can introduce an FMA here. And I will now show you kind of our work in progress theorem statement that we obtain for this example optimization. The first part of the theorem is if we run the optimized Doppler program, there is a word W which is printed to standard out. So this is kind of the CakeML correctness once we add IO code around it. Then we get a proof that the unoptimized Doppler kernel, so the initial program, also returns this W, which is Icing's backwards correctness proof from before. And now comes the cool part. The roundoff error of the optimized program is upper bounded by the user provided bound 2 to the minus 10. And we prove that using existing static analysis tools for roundoff errors, existing static analysis tool for roundoff errors called Flover. And you have to take this with a grain. Yeah. And this is our kind of work in progress theorem that we can prove. To conclude, I've given you an overview of our work in progress integration of Icing into the CakeML verified compiler, which is why I call it putting the icing on the cake here, because it gives us a fully verified optimizing compiler for floating points. And with that, I would like to conclude, and I'll be happy to answer any questions.